Hello, welcome to Coffee Break with Microchip Technology. Coffee Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Latfelter. Joining me in the studio today is our moderator, Aliyah Fahout.
Hi everyone, we are currently live on YouTube, Facebook, and LinkedIn, and you can participate in today's episode by leaving your questions in the comments, or you can email us at livestream@microchip.com after the broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Eric.
Thanks, Aliyah. Our topic today, Jumpstart Fast DC Charger Development with mSiC Technology. Joining us from Microchip's Detroit Automotive Technology Center is application engineer Ehab Tarmoon. Ehab, welcome to the program. All right, let's get started. Now, EV chargers are extremely complex systems. So we're going to focus on the power stage, but before we do that, would you give us kind of an overview of just some of the key technologies or the range of technologies that are involved in EV chargers?
Definitely. You look at EV charger, it has so much technology that goes into it in order to do its function, which is charge a vehicle safely and reliably. And all these technologies have to work together seamlessly. And so when you pull up to a charging station and you walk up to it, the first thing you see that a user will see is the graphics display. The graphics display, and it'll have a touch screen. And that touchscreen needs to be processed, and so a lot of times a Linux-based microprocessor is used in order to process the touchscreen. And then that same microprocessor will be used to talk with the charging system. So usually there's an upstream charging controller that will coordinate all the charging with the different charging stations, and that's through an open charge point protocol stack that is also implemented in that MPU. And it can also be implemented in a 32-bit microcontroller using bare metal programming. So there's different ways you can do that. And then there's the connectivity to that charger management system, which is usually a TCP/IP-based protocol, which could be a hardwired Ethernet connection. You have cellular and also Wi-Fi. There's different ways you can connect upstream to share different types of information. And then you look downstream to the vehicle itself. How does the charging station talk to the vehicle? There's different protocols for that. So there's a well-known standard called CHAdeMO, and that uses a CAN interface. And then there's a more popular now CCS, which will use a PLC, power line communications, using the home plug green PHY interface, where there's communication over the pilot wire to the vehicle. So you have that handshaking and communication, and that's how you establish a reliable communication with the vehicle. So there's communication upstream, downstream, and then there's the billing aspect. You need to have very high precision, high performance, metrology grade metering devices that can measure three-phase voltages and currents and power and energy in order to have accurate estimates for energy and for billing purposes. So there's a lot of technology, and then there's a trend to include an energy storage system within that charging station. So that includes batteries. So you would need a battery management system in order to check the state of health, and have that cell monitoring and balancing if needed. So a lot of technology, and that's aside from the power stage, which is our focus today.
Right, so with the power stage, what are the main subsystems within the power stage?
Yeah, there's two main blocks. Two cascaded converters. The first one is a rectifier. It's a power factor correction rectifier that does the AC to DC conversion. And then that feeds the next stage, which is a DCDC converter, typically an isolated DCDC converter that will take the output of that PFC and output a DC voltage to charge an electric vehicle battery. We have two designs we want to talk about today. They were developed by NC State, that's North Carolina State University, through the Power America initiative, and we would like to discuss those today.
All right, so thank you to NC State. Well, let's take a look at each one of these individually. So first, the PFC stage. Go ahead, give us a deep dive. What's going on here?
Yeah, so the purpose of a PFC first is to rectify that three-phase input. and provide a DC voltage. But you want to do that with a very with a power factor of 1. You want to do this very efficiently so that the power factor is very close to 1. And then the other function of a PFC is to ensure that it has very low total harmonic distortion, which I'll talk about in a minute. Now, our design uses a Vienna topology, and this is a 3-level topology that allows you to use lower voltage rated devices, which will help in terms of performance and cost. It takes in a 400 volt 3-phase 50 or 60 hertz input and outputs 700 volts DC. That's the function of this, and it has to do it very efficiently, and it does. As you can see, the efficiency is 98.6%. The power factor is 0.999. So upstream, from the utility side, it looks like a resistor, very resistive load where it has just real power, no reactive power that's bouncing back and forth. And that's in terms of the power factor. And then in terms of the total harmonic distortion, it's under 3%, which is really low for such a high power device. There's regulations on how low, on how high it can be. And in our case, it's under 3% at full load, and at half load, it's under 5%, which is the typical standard. And we're able to achieve this through digital power, which we'll talk about as well in a minute. The other thing is what's enabling that high efficiency is our mSiC MOSFETs and diodes. We use 700 volt, 15 milliohm discrete devices, discrete MOSFETs, and 1200 volt, 50 amp silicon carbide Schottky barrier diodes. And with these, we're able to establish a very low loss, low conduction loss, and low switching loss. Now, some novel things about this design is that it has a very small, tight commutation loop, which allows for very low inductance, and that helps reduce the switching losses in the converter. We also have a very low thermal interface, thermal resistance for the thermal interface material. So between the case of the MOSFET and the heatsink, we use an aluminum nitride insulator and phase change material, and that really helps decrease the maximum junction temperature of the MOSFET, and that's what's enabling this high efficiency. And then we also have a DS-PIC digital signal controller, and it's a dual core device where the primary core has all the housekeeping functions, and the secondary core has all of the digital control. So the Vienna topology, in terms of the control scheme, is not trivial, but we're able to make it very easy for our customers to implement with our software and our controls that we provide.
Okay, so let me ask you 2 little follow-ups about some of the key components there. First, you mentioned the peak efficiency, which is quite high. Is it the switching, the low switching and conduction losses of the silicon carbide components that ultimately enable that high efficiency?
Yeah, definitely. You could do this with silicon, but you won't be able to achieve such a high efficiency. With silicon carbide, it's able to block that high voltage with a much thinner layer within the device, within the MOSFET structure itself. And that allows for much lower switching losses. And it allows for much lower conduction losses because the RDS(on) is lower. And then on top of that, you know, if you're familiar with silicon, the RDS(on) goes up by a factor of 2 to 2.5 over temperature. With silicon carbide, with our 700 volt devices, it's about a 20% increase. So the RDS(on) isn't even going up very much. On top of that, silicon carbide has a much higher thermal conductivity. You're able to pull and draw that heat out of the die much more effectively than you can with silicon. And there's some other benefits too when it comes to silicon carbide, but it's a big contributor to this high efficiency, and also the switching frequency of 140 kilohertz. We're able to do that, which also enables reducing the size of the magnetics. So it's not just the device itself, but at the system level, there's a lot of benefits too.
Sure, thanks. Okay, and the second follow-up there is just about the digital signal controller. So you mentioned that is a dual core. So I just wanted to clarify, right? So we've got dual core, we've got all the peripherals and the firmware, one piece of silicon, one package. So really a subsystem in a package.
Yeah, it's a really nice device because it really integrates a lot of features and functions in one chip.
Okay.
You have these two cores, but the device is basically a microcontroller with all the peripherals that it has and a DSP, digital signal processor, combined into one chip. So in terms of the peripherals, there are several peripherals that are really geared for digital power. You know, our DSPICs are well known for motor control, for sensing, advanced sensing applications, automotive applications, but where they really shine is when it comes to digital power. We have very high performance peripherals. The PWM peripheral has a very high resolution of 250 picoseconds, and that really allows the regulator, the controller, to regulate the output voltage, so it's very stable, very little jitter, and have that real control of the converter itself. And then you have the DSP functionality where you can implement digital filters, transforms, different types of digital processing within the device. It has 40-bit accumulators. It has the ability to do 100 million multiply accumulate computations in a second. So very high performance, all in one chip.
All right. Interesting. All right, thanks. So let's move on to the DC-DC converter stage. Can you give us an overview of this stage?
Yeah. So this is a 30 kilowatt isolated DC-DC converter using our mSiC devices. It has an efficiency of 98.5%. Now we're able to achieve that for a few different reasons. The way it was designed is that we have, so it's a phase shifted full bridge, but there's actually two of them. We have these two H bridges that are operating, each at a duty cycle of 50% and 180 degrees phase shift, okay? Now, there's only one control variable, though, and that's the phase shift between these two H bridges. So that one variable is all you need to control the output. This converter takes in the 700 volt output of that PFC and outputs a voltage range between 150 to 650 volts. And that's a very wide output voltage range, especially for an isolated DC-DC converter. Now, one of the benefits, the big benefit of this topology is that we're able to maintain ZVS. That's zero voltage switching, which is a type of soft switching. And that essentially eliminates or significantly reduces the turn-on losses. And with that, we're able to achieve ZVS over the entire operating range, even with no load. Typically, with a phase-shifted full bridge, a resonant version of that would require a minimum load to maintain soft switching. In this design, even with no load, you're able to maintain that soft switching. Another nice feature of this design is it has an active snubber. Typically, when there's an overshoot, you capture that energy associated with it and you dissipate it as heat using a snubber circuit. And this design is an active snubber, so we're taking that energy and dumping it into the output, which is the load. So we're using that energy, we're not wasting it, and we're able to get about a 0.5% increase with using the active snubber. Now, our devices that we're using are also discrete devices. We have 1200 volt, 25 milliohm SiC MOSFETs, and 700 volt, 50 amp silicon carbide diodes. And that's how we're able to achieve this very high efficiency. In terms of the controller, we have a DSPIC again, and we provide all the control software for both this DC-DC converter and that PFC you had just talked about. We provide all the design files, whether it's the Altium the schematic, the layout, the bill of materials, the Gerber files, and the software, so that customers can take these designs, send them out to get built, and then can evaluate it.
Okay, my follow-up here would be, why is there such a wide output voltage from this stage?
Yeah, typically there are 400 volt systems. Electric vehicles will have 400 volts, but when we say 400 volts, it doesn't mean exactly 400 volts. There's different ranges for each vehicle. So you may have a max voltage of 420 and a minimum of 300, or the minimum might be a little lower, maybe around 200 or 250. Now, the standard initially used to be a minimum voltage of 150 volts, and it has since increased, but we maintained it at 150 volts. There's also different operating modes the vehicle can be in as well. So you can power a heater, a battery heater from this charger to heat that battery pack up before actually starting charging mode. And that can be done at a lower voltage, like, such as 150 or 200 volts.
Sure. Okay. Thanks for the overview of that section. Now, you mentioned the reference design and the files. You mentioned the firmware and the software. Are there other tools that we provide to simplify the design process? Yeah,
we have a tool called, we work with a company called Plex. So we have a design of their Vienna PFC using Plex. Now, Plex, if you're not familiar with it, it's a power electronics simulation tool meant for simulating power electronic circuits and larger power electronic systems. And with that, it's actually a multi-domain tool. So you can simulate the electrical domain, the controls domain, the thermals domain, magnetics domain, and the mechanical domain, all 5 of them simultaneously. So it's a very powerful tool. And what we did is develop a model for a Vienna PFC that customers can use. So they may take our designs and send them out to get built exactly as is, or they may modify it. They may want to change the packaging, change the input and output voltage range, change the power capability. So the first thing they would do is take this model and modify it to what they're looking for. And then they can estimate the losses of our devices. All right, will the device work? Will it need to change to a different RDS(on) rating, for example? And so we're able to get a lot of thermal information efficiency using this model. It also has the ability to do processor in the loop. So we use our DSPIC PIM card, which is a plug-in module, to communicate with Plex over a USB interface. And with that, you can actually run the controller in the DSPIC, or you can run it on the actual Plex software itself. And you're able then to test the stability of a system, to see how well it performs. You can adjust the tuning. So it gives you all this capability without having to take your initial sample, test it in a lab at high voltage. You can first do detailed simulation work. So it's a very powerful tool in the development of these high power and high voltage systems.
Excellent. Would you remind our viewers about our SiC portfolio? I know we're very well known for the PIC microcontrollers and the DSPIC signal controllers. Would you give a quick overview of our silicon carbide technology?
Yeah, so when it comes to silicon carbide, some might be a little scared to work with it because it switches so quickly. If there's parasitics in a circuit, it may excite all those parasitics. So what we do is we work with our customers. We want them to be able to adopt silicon carbide into their designs with ease, speed, and confidence. So we have a broad portfolio of silicon carbide solutions. You can see we have die, discrete, and modules, and we have gate drivers. And we work with customers to ensure that their designs are driving the silicon carbide MOSFETs properly, that their circuit is designed properly, and that overshoot that occurs, that turnoff, is managed so that it's not so high and you don't have so much ringing. So we work with customers in doing that, and we also have different design tools available. We talked about Plex. We have also SPICE models. We have Plex component models as well. And then online on our website, there's a free online simulator that we call MPLab SiC Power Simulator. And what that lets you do is select a topology, you enter in some basic information on your circuit, and hit simulate, and you get all this information about losses, and you see different waveforms. So it's a very nice tool that is available to our customers.
Okay, so if customers and our viewers wanted to get more information about the portfolio or the design tools, where would we send them?
It's very easy. It's microchip.com/SiC. And there they can find everything, our portfolio, our design resources, and tools.
All right. Ehab, thank you so much for sharing some of your expertise on the EV charger world. At this point, let's go to Aaliyah and see if we have questions from our viewers today.
Yes, we do have one question online. This one is coming from Simon. Can the Vienna PFC be used for bidirectional power conversion?
So the Vienna, by its very nature, is a unidirectional converter. So it takes the AC, converts it to DC, and in that circuit, we use diodes. To make it bidirectional, the diodes would need to be replaced with silicon carbide MOSFETs. And so if you do that, then the hardware will be capable of bidirectional power flow. The control scheme is a little more complex, but it'll give you that very low total harmonic distortion, which is the main benefit of a Vienna or a 3-level type of topology.
Awesome, thanks. Next question is coming from Michelle. Do the reference designs scale to higher power, such as 60 kilowatts?
Yeah, so we're using discrete devices today on our 30 kilowatt design. Going to 60 kilowatts will likely drive you into using a power module, which we also have different power levels for our SiC power modules. But yeah, it's easily scalable for the higher powers using modules.
Great. Next question is also online from Parth. Are simulation models available for your SiC MOSFETs?
Yeah, as I mentioned, online we have device models that are SPICE-based models that work with our tool Mindy, but also other SPICE-based simulators. And also we have Plex models for our discrete devices and our power modules. And those really are helpful because the models are based on actual empirical data. A lot of times with switching losses, you're not really sure how accurate it is. Well, our Plex models are based on actual lab measurements using double pulse testing at different operating points. So it's a lookup table based approach for determining switching losses.
Awesome, thank you. Next question online from LinkedIn is from Sneha. What trends do you see in this space, and what solutions does Microchip offer to support these trends?
Yeah, so one of them was mentioned already, going to the higher powers. Currently, you see a lot of 30 kilowatt converters, and they're stacked to 150 kilowatt for that charging station, or even higher to 360 kilowatts. So going to higher powers is one. Another one is also bidirectional power flow. So in some cases, especially residential charging stations, you might want that power flow to do vehicle to load, vehicle to home type of power transfer, or you eventually be able to sell that power to the utility provider. A third one, which is starting to gain a lot of interest, is medium voltage chargers. This is where instead of connecting to a 400 volt 3-phase or 480 volt 3-phase distribution voltage, to connect to the medium voltage, higher voltage of 6.5 or 13.2 kV, and that lets you eliminate that big bulky 50 or 60 hertz transformer. And so now you can have essentially a solid state transformer within this charging station going from that very high voltage of 13,000 volts directly to your battery voltage of your vehicle at 400 or 800 volts. To support those type of designs, the SiC devices will need to be higher than 700 or 1200 volts that are typically used in chargers. Instead, you would use devices such as 3.3 kV, which is also devices that we have released as well. We have discrete and die available at 3.3 kV, and with an RDS on as low as 25 milliohms. So those are great devices for those type of higher voltage chargers.
Great, thank you. Another question, actually this is our last question. This one's coming from Mandy. Can SiC MOSFETs be parallel to achieve current capability?
Yeah. So nice thing about silicon carbide MOSFETs is the RDS on, it does go up with temperature. It doesn't go up very much, but it does go up. It does have a positive temperature coefficient. And with that, you're able to parallel devices. You don't have to worry about one MOSFET hogging all the current and then going into a thermal runaway. It will be able to balance all the devices. So that lets you scale to higher powers by putting devices in parallel.
Thanks, Ehab. And those are all the questions I have for you today. And for the audience, if you have additional questions, you can email us at livestream@microchip.com. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Eric.
Thanks, Aaliyah. Thank you again, Ehab, and thank you to our viewers for taking some time out of your day to join us today. Please visit us at microchip.com/coffee break. You can see our upcoming sessions, sign up for notifications, and browse our library of previously recorded sessions. Thanks again. See you next time.